In this video, we're going to take a look at equalizers. So equalizers are the next on our list of categorical constructions that we're going to go over. And it's a categorical construction over a diagram of this sort here. And when it's fully fleshed out, this is what it looks like. But let's go back and review some terminology and build up the definition a little more slowly. So what is a categorical construction again? Well, we said it was a limit or a co-limit over a certain diagram. So depending on what this diagram D looks like that we're taking our limit over, we'll call it a different sort of categorical construction. And last time, the categorical construction we looked at was a product where the diagram was very simple. It was just objects and their associated identity morphisms. There were no morphisms going between the objects within the diagram. So this time, we're going to change that, and we're going to actually add two parallel morphisms to our diagram. So instead of our diagram just being consisting of objects and their identities, we're actually going to add two parallel morphisms going from A to B, call them, say, F1 and F2. And we're going to ask ourselves what it would look like to have a limit over this diagram D. So remember that a limit is a terminal cone in the cone category over this diagram. So if any of that terminology is unfamiliar, just go back and look at some previous videos. But so this time, with these parallel morphisms in place, well, first we need to have that our limit is a cone over this diagram. And so here, for example, say we have two morphisms, maybe call them E1 and E2 for equalizer. Well, what would it mean? And maybe our object here will be E. What would it mean for this triple here to be a limit over this diagram? Well, we know that we need to have one morphism going to each object, so we're good there. There's one morphism going from E to A and one morphism going from E to B. And we also need to check the commutativity property of the cone. So in order for it to be a cone, we would need to have that any triangle formed between the legs of the cone and the morphisms in the diagram need to commute. So for example, here we have two legs and two morphisms in the diagram. So there's two triangles that need to commute. We need to have F1 after E1, F1 after E1 needs to be equal to E2, and F2 after E1 also needs to be equal to E2. And if we have these two equations in place, then we have a cone over this diagram. But that means that E2 is actually a little redundant here, because even though we drew it like this, we see that E2 is actually effectively just this morphism. So really, we could have drawn this diagram completely without E2 at all, because it's already represented in this diagram by these morphisms here. So if we were to redraw that, we could have it as a little bit more of a sort of flat visualization, where we have, say, maybe instead of E1, now we can just call it E, coming from our object E into our diagram D here. And what is our diagram D? Well, it consists of two parallel morphisms, F1 and F2, both going from A to B in our diagram here. And since these are just equal to each other, we can just replace this condition here with saying that F1 after E1 has to be equal to F2 after E1. So it actually simplifies our cone a little bit. Our cone can just consist of one morphism in a sense, right? Because the other morphism we get for free. And sorry, this should be just E now. So it was E1 here, but now since there's only one morphism, we can just call it E. So the pair E, capital E, lowercase e, sort of forms a cone over this diagram because there's an implicit second leg that gets created thanks to simply the commutativity property that we need for a cone. Now, if this cone also happens to be a limit over this diagram, so i.e. that means this cone is a terminal cone in the cone category over this diagram, then we have what we call an equalizer. So we'll write down the definition in a second, but that means that an equalizer is a limit over a diagram with two parallel morphisms in it. In this case, F1 and F2. So what would another cone look like in this case? Well, we saw that cones over this kind of diagram only need to consist of a single morphism because of that commutativity property. So we'd need to have that for any object x and morphism, say, little x, going from x into a, where this diagram commutes with this morphism x. That is, we need to have the same property as E, so we'd need to have F1 after x is equal to F2 after x. And if that's the case, then we must have a unique cone morphism theta going from x into E. This is our theta here. Such that, so this goes from x into E, such that, of course, this triangle here commutes. That is, we can factor x through E in a certain sense. We can, for any x, we can factor it through E using some sort of cone morphism over this diagram. So that would be, in this case, x is equal to E after theta. So to sum up our discussion, an equalizer is a limit over a diagram consisting of two parallel morphisms. So of course we need to have two objects A and B in our diagram D, and two parallel morphisms going between them. And if we have a limit over this diagram, then we call that an equalizer. Just like when we had a limit over a diagram with no morphisms and only objects and identities, we called that a product. So in this case, with the two parallel morphisms, we call it an equalizer. And what does that mean? Well, we saw that it was a double this time. Usually we're used to triples, like our product was a triple, but here it's just a double for the reasons that we saw earlier with the commutativity property over these parallel morphisms. And they have to satisfy these two properties here. So if you have a double in your category that satisfies these properties here, this is number one, which guarantees the commutativity property, and this is number two, which guarantees that it's a limit that is a terminal cone, then you have an equalizer. And if that's the case, we call this the equalizer morphism, the second half of that pair. Our first result involving equalizers will be to show that that equalizer morphism is actually always monic for any equalizer. So what does monic mean again? Well, monic means left cancelable. So that is anytime we have a G1 and a G2 both going from X into E here, G1 and G2. Anytime we have that, we must have where their composition with E is equal. So that is E after G1 is the same as E after G2. Then it must be the case that G1 is equal to G2. So pretty obvious why it's called left cancelable. We have E on both sides of this equation on the left hand side, so we can just cancel them out and end up with G1 equals G2. So how do we prove this? Well, let's suppose first what our initial condition is. So suppose E after G1 is equal to E after G2. So that goes from X to A, obviously, right? E after G1 and E after G2 both go from X to A. So let's just write it here. This morphism here is E after G1, which is the same thing as E after G2. Well, then it's pretty clear that X together with this morphism forms a cone over D, because if we look at this chain, E F1 after E after G1, well, F1 after E is equal to F2 after E, right? Because E is an equalizer morphism for F1 and F2. So this is just F2 after E after G1. So this E after G1 morphism here, which is the same as E after G2, forms the morphism in the cone over D. But then that means, because the equalizer is a limit, that we must have a unique mediating morphism, theta, going from X to E, such that E after theta is the same as E after G1. But there's only one morphism where that's the case, which is G1. Right? It's already in this form, so if there's only a unique one that satisfies this, then it must be G1. And we also have that E after theta is equal to E after G2, because this is equal to E after G2. And so that's the same. We must have theta equals G2, but then combining these, we have G1 equals G2, which is exactly what we needed to prove. So that's QED. And that shows that anytime we have an equalizer, then the equalizer morphism, E here, is a monic morphism. It's always left cancelable. To understand these equalizers a little bit better, let's look at how they would work in a category with set-like objects. So, for example, the category of sets, the category of groups, the category of rings, the category of modules over a given ring, etc. So, if it makes sense for us to talk about elements of our objects, so if all of these objects here are actually some sort of set-like object with elements in them, then if E, uppercase E, lowercase e, is an equalizer for F1 and F2, as we've drawn it here, then it must be the case that E F1 after E is equal to F2 after E, right? Following this chain needs to be the same as following this chain. And if now we have objects inside of our if we have elements inside of our objects, which are sets, we can say that f1 applied to e of x needs to be the same as f2 applied to e of x. And this is for all of the elements in E. So this chain needs to be the same as following this chain, and that's true for all of the elements that might be living in this set-like object here. Now, what does this expression actually tell us? It says that composing F1 with E is always the same as composing F2 with E. So what that means is that E can only map to values in A where that value in A gets mapped to the same thing by F1 and F2. So the only thing that E can send elements of E to are elements of A where F1 and F2 agree on that element. So obviously F1 and F2 don't need to be the same. They could map some other element that E does not map to different things, because that won't matter. When we do the composition with E, we'll only arrive at values where they do agree, and so this chain will be the same and this chain will be the same, even if these two aren't necessarily the same. So just to illustrate that a little bit better, let's say we have our set-like objects E, A, and B here, same as here, E, A, and B. And let's say E has two elements like this, which get mapped by E into A, which has three elements, and that gets mapped by our two morphisms F1 and F2 into B. Well, if we look at this pattern here, E maps to this top element and this bottom element. And on both of those elements, F1 and F2 send that element to the same thing. So sends it to the top one, which agrees, F1 and F2 agree, and sends it to the bottom one, where F1 and F2 agree. However, it does not send any elements to this middle one in A, which does not agree from F1 to F2. So in this case, F1 and F2 are not equal because this element maps to different elements in B, but the composition of E with F1 or E with F2 is going to be the same because all of the elements that E maps to agree on F1 and F2. So this is enough to guarantee the commutativity property, so we know that EE is a cone over this diagram here. But how do we know that it's a limit when these are set-like objects? So if you want to think about it for a minute, maybe pause the video and decide how would we guarantee not only that this commutativity property holds, as we've demonstrated here, but also that this is a terminal cone over this diagram. This is a limit. EE. Well, we would need to have that for any other cone over F1, F2. So for example, we could have this singleton X here with just a morphism going into this top element here because this top element agrees. So the commutativity property holds. And we know that X is X and this morphism here, which we might call H, form a cone over the diagram D as well. So what we would need would be a unique morphism going from X into E, right, our theta here, a unique morphism going from X into E, call it theta, such that the triangle commutes, of course, so that such that we have H equals E after theta. But in this specific case, with the cone XH, we're good because there is only one way to assign theta to each element of X, only one, this one element here. there's only one way to assign it so that this triangle commutes. So this function exists and it's unique, right? Because if I were to try to assign it to this, well, that's not going to work anymore, right? This triangle is no longer going to commute. So in this specific case, there would be a cone morphism, which would be required for this to be a terminal object. But we need to know that every possible cone over D has that cone morphism, that theta going from that cone to E. So to know whether it would work for every possible cone over D, we have to think what would be the case where it wouldn't work, or what would be the cases where it wouldn't work. So the first case where it wouldn't work would be, say that A had some other element here. Say, so now, for now, this element is part of A. So A has 4 elements. And say that A also, that F1 and F2 also map this element to the same thing. So F1 and F2 agree on what they send this new element to. And say that instead now, H didn't send it to this top element here, but sent this singleton element to this new object. Can you see what would happen there? So this new element agrees for F1 and F2. They get sent to the same thing. So the composition of H, this new H with F1 and H with F2, would still be good. So this would still be a cone over this diagram D, right? Because the property that this composition is equal to this composition would hold. However, little e does not send any element in big E to this new element. So I haven't changed what E does. E still sends it to these two. And E is still a cone, right? These ones agree and these ones agree, and they only get sent to elements where they agree. But now this triangle no longer commutes, right? This goes to here and this goes to here. So you can see it doesn't even form a triangle anymore, right? So the commutativity property for the mediating morphism here has been broken. So that would be the first case where this commutativity property would no longer work. H would no longer be equal to E after theta. The other way this mediating morphism property could fail would be if this commutativity property held and there did exist a theta which allowed this triangle to commute, but suppose this theta was not unique. So suppose there were some third element in E which little e mapped to the same top element as this top one here. Well then, all the commutativity properties hold, right? This is still a cone, XH is still a cone, EE is still a cone, and there is a theta that allows this triangle to commute. However, there's actually another theta that allows that triangle to commute, right? If I assign by theta 2, say, this element to this one, well now this triangle still commutes, right? There's still no problem because these ones both sent it to the same element here at the top. So if this were the case as well, this property would no longer hold. This would no longer be a mediating morphism because it would not be unique. So we've seen the two problems that could prevent us from having this mediating morphism property hold for certain types of cones. So we need to ask ourselves, how do we avoid those two problems? So there's two problems. Either this theta doesn't exist at all, there's no theta that allows this commutativity property to hold, or there is a theta that allows the commutativity properties to hold, but it's not unique. There's another theta that allows the commutativity properties to hold. So how do we resolve those two issues and ensure that those don't happen so that we can guarantee that this is in fact a limit? Well, let's deal with the second one first. So as an exercise, pause the video here and ask yourself, why is this actually a non-issue? So the second one is the one we've drawn out here, where we have a mediating morphism theta, which allows this triangle here to commute, but we also have another one, which allows this other triangle here to commute. So why is this actually a non-issue? Well, to answer this, we can apply the result that we proved just a little bit earlier, which is that equalizer morphisms are always monic. So what does that mean? Well, E here, little e, always has to be monic. And what does monic mean in the case of set functions and homomorphisms on set-like objects? Well, it means that it's injective. And the whole problem with this situation here was that E collapsed two elements in big E to one element. And conveniently or inconveniently, that was exactly the one that H mapped to. So that was what created the problem. But if our mapping were injective all the time, then we could never have this sort of collapsing pattern, and we could never have more than one mediating morphism that would allow this triangle to commute. So the first one is actually a complete non-issue, thanks to the fact that this E is always monic, i.e. injective. We can actually use the fact that E is monic to deal with the first problem as well. So if you recall, the first problem was that there might be some element of A out here, which H maps to, like this, and on which F1 and F2 both agree. And if that's the case, then this commutativity property didn't hold, we said, right? The triangle is broken here. So to deal with that, since we know that E is monic, we know that it's going to take on as many values in A as there are values in E, right? Each value in E gets its own value in A. And so we can kind of just use a cardinality argument, right? We can just say that in order to deal with this problem of having an extra element out here, we need E to be at least as large as the largest object in A on which F1 and F2 agree on all the elements, right? So in this case, what would be the largest object in A? And in this case, we're talking about sets, let's say. What would be the largest object in A on which F1 and F2 would agree? Well, it would be this element, and this element, right? So that's 3 elements, and our E here is only 2 elements large. So it wouldn't satisfy the criteria, right? We would need to have some third element of E here that E mapped to this value here, right? So we basically just use a cardinality argument. Because E is monic, we know it's going to take on as many values as there are values in E. And so we just say, well, whatever the largest object in A is, on which all of the elements F1 and F2 map the same thing, that is, F1 and F2 agree on all of the elements in that object, then we just need to make sure that E is at least as large as that object. So we can conclude our discussion by giving an explicit description of what an equalizer would look like in a category with set-like objects such as set, group, ring, or mod. So we said that E would have to be at least as large as the largest object contained in A on which F1 and F2 always agree. But we could make things simple on ourselves and just say, let's just make E part of A. Let's just say E is all the values of A in the largest object contained in A on which F1 and F2 always agree. So if that's the case, then we can take E to be the inclusion map from E to A. So the inclusion map just picks out all the values of E in A. So it takes any value X and just returns X in A. And if that's the case, then for any cone XH over D, H will only map to values of E in A. It's only going to map to values where F1 and F2 always agree if it's a cone. And so we can define H prime to be the exact same function, but we just map it into E instead. So this one's going into A, but it's only going to go into values of E that are in A. So we can just define the exact same function going into E instead. And we'll see that H prime in that case would be the mediating morphism for H. So we kind of went through that in a bit of a more diagrammatic way and a little bit more informally. So if you want a good exercise to conclude here would be to prove this a little more rigorously. So write down the proof in words rather than just in diagrams of why this statement is true.